This month, we're at the National Space Centre in Leicester.
Home of a magnificent vertical rocket display and the largest planetarium in the country.
The centre is 20 years old this year, and August 2021 marks the 10th anniversary of NASA's Juno probe setting off for Jupiter.
Welcome to the sky at night. If you're looking for somewhere to take the kids or the grandkids this summer holiday, this is the solar system. We've come a long way since our ancestors looked up in the night sky and saw wandering stars. We now know that those aren't stars at all, but planets. The advent of the telescope enabled us to see them in much more detail, and the 20th century allowed us to send probes, getting an even better understanding. This programme is all about one of those probes, Juno, NASA's mission to Jupiter.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
Juno was launched 10 years ago on the 5th of August 2011. But its mission proper started 5 years later, in 2016, when its thrusters fired it into its orbit. A triumph for the Juno team, as Chris experienced.
There it is. There we go. Juno right on time, into orbit, exactly as planned. We have a spacecraft in orbit around Jupiter. I think people are rather pleased.
Juno wasn't the first spacecraft to travel to Jupiter. Back in the early 1970s, 2 Pioneer spacecraft collected images. And in 1979, the twin Voyager spacecraft sped past on their way to the outer solar system.
Good evening. As I think many people will know, the Voyager 1 probe has made its pass of the giant planet Jupiter. And this is a film made up of the various stills taken as the probe went in. And you can actually see Jupiter spinning round. And there it is, there's the great red spot below the center.
Our views of Jupiter and its moons have changed completely since the days when Patrick was reporting on Voyager. And so I've come here, to the Space Centre's planetarium that bears his name, to talk to the Juno scientists continuing our quest to understand the giant planet. Lee Fletcher, one of the UK scientists attached to the Juno mission, is based down the road at the University of Leicester. Lee, thanks for coming. It's wonderful to be able to enjoy Juno's images in full cinematic planetarium glory. So let's fly over Jupiter and you can tell me what we're looking at.
So as you know, Jupiter is this enormous ball of hydrogen and helium gas with a mixture of other condensables mixed in with the cloud tops. And that's what forms these beautiful swirling patterns that you can see. And maybe the reason why Juno is so there in the public eye are these exceptional images that it's been returning for 5 years now.
Well, let's take a look at some close-ups. Let's start in the middle of the planet. This is the equatorial region.
Yeah, and the equatorial region might be familiar to any amateur astronomers as normally being this stripe of white sandwiched between 2 narrow bands of brown and red. And yet, every 6 or 7 years or so, a bizarre event takes place which replaces those white clouds by this strange red, ochre, orangey type appearance, almost like an orange filter through which we're seeing the deeper dynamics. And very recently, Juno captured this stunning image looking right down at the equator.
Let's travel to a different bit of the planet. Now this I recognise. This is the famous red spot.
Now, you can't send a mission to Jupiter and not do some detailed studies of the Great Red Spot. A huge swirling storm that's been there for at least 150 years, if not even longer. Now, the Great Red Spot is at its smallest it's ever been in human history. And what you can see in this selection of images over several Juno encounters is that some of that red material is being pulled off of the vortex. It's being extruded by other passing anticyclones nearby. And the question, of course, is that destroying the Great Red Spot? Will it lead to its demise? Now, some investigations over the past 12 months or so are suggesting that whilst this does look like bad news for the Great Red Spot, it's actually a superficial event, that this red material is sat over the top like a mushroom cloud. We're taking material off that, but we're not affecting the underlying
So there's still
vortex.
a deep storm down there. Let's head all the way up to probably the weirdest feature, I think, which is at the poles.
You need a spacecraft to give you these sorts of observations. There's just no way to do it from planet Earth.
So we're seeing these swirling clouds often high up in the atmosphere.
Yeah, you're seeing swirling cyclonic features, okay, that are some 3,000 to 4,000 kilometers across, organised in a pattern that nobody ever expected to see.
We've got, what, a hexagon here? Pentagons.
And hexagons, all surrounding a central polar cyclone that seems locked at the pole. And we're still trying to fathom what is going on.
One of the great mysteries is about water on Jupiter. Why is it important to know about that?
One of Juno's goals was to try to get to grips with the amount of water, the amount of oxygen that's present within Jupiter, because that tells you something about how Jupiter first formed in the solar system. If it's really abundant, it suggests one way of forming Jupiter. If it's underabundant, it's telling you something completely different. To measure water is really hard, and they do it with a microwave instrument.
So where does that leave us with the water story?
We have one measurement at the equator, and what that shows is that water is enhanced over solar composition. So Jupiter isn't just a piece of the sun out there at great distances. It's not got the same chemical composition, but water isn't underabundant.
But that's one measurement.
It's one measurement, yes. And it was a very tricky measurement for the Juno team to make. But now they have plans and work is in progress to try and extend that measurement across Jupiter to find out whether the equator is somehow unique or whether that does represent Jupiter's genuine water abundance.
But if that result holds up, that supports this idea that Jupiter formed in a protoplanetary disk, right? Like other planets.
And crucially formed from the accretion of some kind of core to begin with. Then it's sucked in all the surrounding nebula gases. So it's starting to point to this idea of what we call core accretion as being genuinely the reason why
you form a tiny rocky planet and then it gets out of hand.
Exactly.
And we'll look forward to more news in a year or two. Thanks for spending time on Jupiter.
You're very welcome.
Juno's remarkable discoveries include the revelation that between Jupiter's veil of ammonia and its rocky core lies a thick layer of liquid hydrogen, so compressed by Jupiter's mammoth gravitational field that it's become metallic and conductive.
But while much has been explained, other mysteries remain. Johnny Nichols has been investigating Jupiter's auroras since the start of the Juno mission. Johnny, you've been working on Juno data right from the get-go, but I'm quite interested to see what the differences are between the aurora we see on Earth and the aurora we see on Jupiter.
Yeah, so the principal difference is the source of the energy. The energy that drives the Earth's auroras principally comes from the sun and the solar wind, which emanates from the sun in all directions. And it hits the Earth's magnetic field, stirs the magnetic field around, and produces electric currents that flow through the Earth's magnetic field. And that drives the Earth's auroras. The energy for Jupiter's auroras comes principally from the planet's rotation. Jupiter rotates very quickly, once every 10 hours or so, and that energy source drives Jupiter's auroras.
And this is the pole of Jupiter?
This is the north pole of Jupiter that we've observed with the Hubble Space Telescope. And the main ring of aurora there is what we call the main oval or the main emission. And the idea is that the moon Io orbits deep within Jupiter's magnetic field, and it's an extremely volcanic object. Its volcanoes throw out sulfur dioxide at the rate of about 1 ton per second into the space surrounding Jupiter. And that's been emitted into the very rapidly rotating magnetic field. This material becomes ionized and is turned into a plasma.
So can we see Io here?
We can see what we call the Io footprint. And on the right-hand side of this picture here, you can see almost like a tadpole. There's a blob of, that's the official term, a blob of aurora with a tail extending up towards the top.
So can we look at that in more detail?
We can. This image on the right-hand side is a zoom in on the Io footprint. And this was taken by the Juno spacecraft in the infrared.
It's really quite lumpy, isn't it?
It's really lumpy. And the reason why we think this aurora occurs is it's superficially similar to what we call von Karman vortices. If you stand on a bridge and look down into a fast-flowing river, you'll see eddies behind the pillars of the bridge. And you can almost see the eddies behind Io. What we think we're seeing is waves traveling along the field lines that have been reflected from the ionosphere and from the region near the moon itself.
So you've been working on Juno data for some years, but before Juno ever got to Jupiter, there were ideas of how the aurora worked. Are those theories being vindicated, or are they being blown out of the water?
Yeah, so the main ideas behind the generation of the main auroral oval on Jupiter is that it's produced by fast-moving electrons as part of an electric current system. Recently, we've seen when the aurora brightens, the currents get really strong. So it looks like there's an association between the electric current system and the generation of the auroras.
Yeah, a loose correlation.
Yeah, so that is really nice evidence to point in favour of these ideas that the auroras are produced by the electric currents. But I think from my own perspective, it seems like the ideas are probably broadly correct.
That's quite encouraging, I guess.
Yes.
So what of the future?
Well, there's so much data here, this will keep us busy for a long time, but there are questions that we can't understand with the data that we've got, and so we'll be looking towards missions in the future.
Well, as you say, there's lots more data to study, so do come back on the programme again and we can sort of find out a bit more about Jupiter's aurora.
Absolutely.
Thanks, Johnny.
While Juno's spectacular views can only be achieved from orbit, from down here on Earth we get the bigger picture. Here's Pete to show us how.
Well, I had hoped to bring you a view of Jupiter through my telescope tonight, but as has been the case over the last few weeks, the sky has completely clouded over now. If you're wondering where Jupiter is, then it's rising in the east-southeast during August as the sky is getting darker. It's a really bright object down there. The problem is that looking at a planet when it's low down, for example, just after Jupiter has risen, will give you quite a wobbly view of it because you're looking through a thicker layer of atmosphere. The best strategy is to wait until Jupiter gets to the highest position in the sky, and that's due south. Mid-August, that occurs around about 1:30 BST, and at the end of August, it's about midnight. Jupiter comes to opposition on the 20th of August, and that's the time when the planet appears brightest and largest when you see it through the eyepiece of a telescope. Now, the weeks leading up to opposition and after opposition will give plenty of fine views too, so there's lots of time to take this planet in. If you have a small telescope, you'll immediately see that the disk looks flattened at the poles, and that's a consequence of Jupiter's rapid rotation. You should also be able to make out the two largest belts. That's the North Equatorial Belt and the South Equatorial Belt. They run parallel to the equator. Nestled in the southern edge of the South Equatorial Belt is that long persistent storm, the Great Red Spot, but you'll need a telescope with an aperture over 4 inches to see that. Larger telescopes will pick out even more detail, more belts, more zones, bright spots, dark spots, and lots of other structures on the edge of the belts and zones. So there's plenty to see there. Now, as well as all this detail, Jupiter has a large family of moons, but only 4 are easy to see with a small telescope. And these so-called Galilean moons are quite interesting. And to demonstrate some features about them, I've made a model. Bear with me a second. There we go. So this is my model of Jupiter. If I bring you in a bit closer, you can see the main disk in the center here, and you can see the 4 Galilean moons either side of Jupiter. Now, this is quite a reasonable model because it shows what the moons sort of look like through a small telescope. And as they orbit round Jupiter, you see the moons moving around the planet. Now, various things can happen. For example, the moon can move behind Jupiter and then it gets occulted by the planet's disk. Or, depending on the geometry of the situation, it can move into Jupiter's shadow, and that's called a moon eclipse. Another effect occurs, if I can demonstrate this, I'll steal a moon for this one. There we go. As the moon moves in front of Jupiter, so its shadow falls on Jupiter's disk, and that creates what's called a shadow transit. And there will be quite a number of these over the up-and-coming observational period. But an interesting thing is happening with Jupiter at the moment, because the planet has just gone through what's known as an equinox. That's when the sun appears on Jupiter's equatorial plane. I can simulate this by dropping the camera down like so that we're looking along the equatorial plane of Jupiter, more or less. And that means that as the moons go round the planet, they can interact with one another. So you may get one moon which covers another, or you may get the shadow of one moon eclipsing another. And these are called mutual events. And over the coming weeks, there'll be a number of these mutual events to look out for. For details of upcoming interactions and advice on how to view what promises to be a spectacular Perseid meteor shower in the next few days, visit the Sky at Night's website to watch this month's star guide.
The Juno mission was originally meant to last for 7 years, bringing it to an end in 2018. But NASA extended the mission till this year, 2021. Now, when we were planning this program, we thought it would be a tribute to Juno and all it's achieved. But earlier this year, NASA announced a further extension of 4 years. Chris spoke to Scott Bolton, Juno's chief scientist, to find out what it's going to do next.
Scott, thanks for joining us. So Juno's just received permission to go for this exciting extended mission. Can you tell us about how the extended mission differs from what you've done so far?
So a lot of it is driven by the orbit. We were an ellipse that was sideways to Jupiter, so to speak. And then over time, Jupiter's gravity field forces our orbit to twist around. And so the part that's closest to Jupiter is moving more and more to the north. And so in the extended mission, that moves from near the equator all the way up to like 60 degrees north or higher. And so that gives us really close views of the northern hemisphere. So it's perfect to study some of the mysteries that we've already uncovered, things that were discovered that the north was different than the south, and it has all these complexities, so we can study that. And now we're crossing the equator near Ganymede, so we got a close Ganymede flyby. Next year, that will continue to move in as this ellipse twists around, and we eventually will get a close flyby of Europa. And then we have 2 close flybys of Io. The other thing that we'll be doing is we'll actually be going closer and closer to the rings. We'll be the first true Jovian ring explorer.
And people will be surprised to hear that, because of course Saturn is the ringed planet, but Jupiter has these very different rings as well. They're very tenuous, right?
They're very thin and tenuous. We don't really know very much about them. We've only got a few glimpses. We took a couple of pictures of those rings early on in the mission and went to a science conference, and the ring community went crazy. So we said, oh, wow, we'll take more of these and we'll map it out. And in fact, we'll go in and do what we call in situ. In other words, the spacecraft will actually go into the rings and we'll measure dust impacts.
I last talked to you just after Juno reached Jupiter orbit. What have been the highlights of the mission for you so far?
Well, one of the highlights, I would say, would when we first got there, right? We were all really excited and curious. When we were also nervous and praying it was going to work. Could we get into orbit, all of that. But one of the most amazing highlights to me was when I saw the very first image as we went over Jupiter's pole. Right? Nobody had ever seen the pole. We didn't know what it looked like. We had this JunoCam camera on there. And even though I'd imagined what I thought were wild ideas, it just looked different. And everybody, I remember the whole team looking at it as we put it on a projector, and we were all like, wow, because here were these giant polar cyclones. And I remember asking one of the atmospheric scientists, how do those get formed? And he's like, I have no idea.
Always a good answer. And if you could have a free card now and know that you were going to solve one mystery, what would you play your card on? What's the big mystery to solve?
That one's hard. If I could solve one mystery. So I think I'm leaning toward the deep atmosphere and wondering about how these giant vortex storms work and how deep the roots go. We see these beautiful images of Jupiter, swirling, beautiful clouds, different colors. And I'm wondering how deep the roots are for like the Great Red Spot versus other vortices, and then these polar cyclones. Now, of course, if you ask different people on my team, they'll give you different answers. And one of the big themes coming out of Juno is that what used to be different disciplines of science are actually being intertwined and are affecting each other. So the old days of exploring with, Galileo or Cassini or Voyager, you had different groups of people, and the people that were studying the magnetic field were different than the people studying the atmosphere or the interior. And while they met and talked, they didn't actually work together. We're finding that things are affecting each other, and our team is becoming more and more interdisciplinary. We no longer actually have separate science discussions in the meetings because everybody wants to hear what the other side is doing because they know somehow it's affecting them.
So there are a couple of future missions. There's Europa Clipper coming up from the US, and we've got our own JUICE mission here in Europe. Are you talking to those teams?
Yeah, we actually are working with both the Europa Clipper team and the European Space Agency's JUICE teams. We're in contact with them. I explained what we were doing both in the prime mission and the extended mission. So we're helping and can complement them in a couple of important ways. One is we're measuring the radiation environment, and they have to go through it. And we're kind of getting ground truth, right? The other is that we're making measurements as we go by Ganymede and Europa. And so we're in constant contact with both teams and sharing lots of data.
The European Space Agency's Jupiter's Icy Moon Explorer, or JUICE for short, launches next year, starting its own unique mission, as the project's deputy lead investigator, Emma Bunce, explains.
The JUICE mission is going to be the first European spacecraft to the Jupiter system, first of all, and it's going to be the first spacecraft to actually go into orbit around an icy moon. It will look at Europa and Callisto during flybys. It will also do flybys of Ganymede, but importantly, will end up actually in orbit around Ganymede.
We just got a new look at your target for JUICE. So this is an image of part of the Ganymede surface from Juno.
Ganymede is a particular favourite of mine and is Jupiter's largest moon. It's the largest moon in the solar system. It's actually bigger than the planet Mercury.
And I think if you showed this picture to people without context, people would guess this was our moon, right? It looks like our moon, but it's a very different world.
Absolutely. I mean, it couldn't really be more different in so many ways.
Here's another image from the same flyby, but we're looking at water ice here, frozen water. That's what the surface is made of.
That's right. I mean, back in the 1960s, ground-based telescopes using spectroscopy worked out that the moons in the outer solar system, including Ganymede and Europa and Callisto, have icy surfaces.
And that's where a lot of the excitement is, what's underneath the crust. So what's our current guess as to what you'd get if you drilled down through this crust?
Well, first of all, you'd have to drill for quite a long way because it's a very thick icy crust, but we do believe that Ganymede is an ocean-bearing moon, which means that we think it has potentially 100-kilometre deep subsurface ocean underneath the icy crust, which is incredibly exciting.
And that's a water ocean as well.
A water ocean, that's right.
So I think we've got a guess, a recent guess as to what's going on. And this is more complicated than that.
Exactly. And some interesting things that we've learned, like the fact that Ganymede has a magnetic field, indicates to us that there must be an iron core and a liquid metallic component to that iron core, which allows a magnetic field to be generated and sustained. And so that gives us clues to the interior too.
Just like Earth's magnetic field comes from an iron core.
Exactly.
But there's also some fun phenomena that happen because of the magnetic field itself. So there's this observed aurorae on Ganymede. This is from the Hubble Space Telescope. What are we seeing here?
That's right. So the internal magnetic field of Ganymede plus the induced field signature due to the ocean then interacts with Jupiter's magnetic field as Ganymede orbits around Jupiter. So there's a lot going on. It's a very dynamic picture.
I think seeing aurorae from a moon is going to be on the tourist list in the far future, I think. I think it's a stunning
It's absolutely
thing.
incredible, and it's unique within the solar system as far as we know. And so again, it's all of those really interesting features of Ganymede that really compelled the European Space Agency to design this mission to go and focus on studying this moon.
Let's pull up a picture of JUICE because it's nice to look at it. What's the status of the spacecraft now and what work still needs to be done?
So it's now in this testing phase and staying on good schedule, ready for launch next year.
And then there's a cruise to get to the system. So when does it arrive at Jupiter?
That's right. It's being launched in 2022 and will be arriving in the late 2020s or just about 2030, and will go into orbit around Jupiter to begin with. It will then spend a few years in the Jupiter tour, part of the mission, studying the planet itself, looking at the moons during multiple flybys. And then the spacecraft will enter this incredible orbit phase around Ganymede.
Given that you're a year away from launch, it might be too early to ask this question, but what comes next after JUICE? What are your grand dreams for exploring Jupiter and its moons?
The way that we have thought about this is that JUICE is the next logical step in terms of our exploration. You know, we've had the Voyager missions, we've had the Galileo mission at Jupiter. Now we're going to have a mission dedicated to orbiting Ganymede and giving us the next level of detail about that moon and its surface and its interior. We need that before we can go any further. So people would like to send landers to the moons of the outer solar system, for example, Europa and Ganymede, but as I'm sure you can imagine, that's extremely challenging. And if you were potentially scoping out landing sites in future, you need to have that information before you can take those exciting next steps. But inevitably, some of the most exciting results will be things that we haven't predicted and we don't foresee. So that in itself is really what planetary exploration is all about.
It also makes it enormous fun to take part in these missions. You must be having a whale of a time.
Let's be honest, that is a big part of it. It is just a huge amount of fun, and it's a real privilege to be involved in these missions.
Juno is by far the most successful mission to Jupiter yet. Because of Juno, we have discovered vast amounts of metallic hydrogen, seen strange cyclonic polar vortices, and have new insights into how the whole solar system formed.
But all that has just whetted our appetite. The next missions to Jupiter's moons will tell us even more about these, our icy neighbours, and maybe even a little about life itself.
That's all from the National Space Centre. Next month, we'll be in Chelmsford for the Sky at Night Question Time programme, where we'll be answering all your astronomical questions in front of a live studio audience.
If you'd like to submit a question or attend the recording, then follow the link that's on screen now. We'd love to see you there. Until then,